Question 10. The live wire in a 3-core cable is connected to a fuse inside a plug. A fuse contains a wire that is designed to melt when the current gets too great. Figure 17 shows a fuse. 10.1. What color is the insulation covering the live wire in a 3-core cable? 1 mark. It's brown. Question 10.2. Draw the circuit symbol for a fuse in the box below. And that is a fuse. That's how we represent a fuse. Question 10.3. The fuse wire melts when there is a charge flow of 2.0 coulombs for 400 milliseconds. Calculate the current in the fuse wire. Use the physics equations sheet. 4 marks. Well, first of all, we need to write down the charge here. Charge equals IT. Q is 2.0 coulombs. And the time, T, equals 400 milliseconds. Milli means 1/1000. So that would be T equals 400/1000. So I've changed the M into 1/1000. And that gives time to be 0.4 seconds. Now we can plug in those values and find the current. But we need to rearrange that equation and make current the subject. I is the current. So I equals Q over T. Now plug in the values. Q is 2, I is 0.4, and that gives 5 amps. So check the unit. It says A for amps, so we just need to put 5 here. Question 10.4. When the fuse is at its melting point, the additional energy needed to melt the wire is 1.02 joules. That's the energy. Specific latent heat of fuse wire equals 60 kilojoules per kilogram. So we're dealing with energy which is in joules, and we got specific latent heat which is 60 kilojoules. So we need to change the K to joules. Calculate the mass of fuse wire. Use the physics equation sheets. 4 mark. Well, so energy Q is the energy here in this case, or you can say E is the energy. Well, we tend to use Q sometimes. And this is going to be 60 times 1000 because K is 1000. So we have to put 1000 there to represent K. So 60 times K, which is 60,000 joules per kilogram. So always watch out for that. They have to be in the same unit. And that L stands for specific latent heat. So to calculate the mass, first we need to write down the equation. That's M for mass. The equation now, the energy here, or E, you could say we tend to use Q as well for energy. Q here equals ml. And we want to make M the subject. M equals Q over L. And we need to populate it with the value 1.02 joules for Q. Q in this case is energy, not charge, divided by the specific latent heat, which is 60,000. So that's 60,000 there. And that gives M to be 1.7 times 10 to power minus 5 kilograms, which means, check the unit, kilograms. So we just need to put that in here. So that would be 1.7 times 10 to power minus 5. Question 10.5. The calculation in question 4 assumes there is no energy transfer to the surroundings. How would the time taken for the wire to melt be affected if some energy was transferred to the surroundings? Give a reason for your answer. So we need to tick one box here. The time taken would decrease, time taken would stay the same, the time taken would increase. Well, it should be that the time taken will increase, so it takes more time because so many energy is lost. And so the reason would be more energy would be needed to be transferred in total because some energy is lost to the surrounding, but you still need the same amount of energy to melt it. So more energy has to be given. So that means you have energy that is melting plus the energy that got lost. That's why it would take longer.